Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to describe some crucial properties of the correlation coefficient which reveal that it indeed quantifies the linear dependence between quantities. Up to now, we have seen that we can build linear estimators that are optimal in terms of mean squared error based on the correlation coefficient, but now we're going to see that the correlation coefficient also encodes the quality of those linear approximations. Let's get to it. So we're going to talk about properties of the correlation coefficient, and in particular there's going to be three very important properties that we're going to describe. First, the correlation coefficient is bounded between -1 and 1. Second, if it equals -1 or it equals 1, it implies complete linear dependence between the two quantities of interest. Third, the square of the correlation coefficient is equal to the fraction of variance that can be explained linearly. When we have a linear estimate of a quantity given the other, the fraction of variance, which is a proxy for the information contained in the estimate, is exactly equal to the square of the correlation coefficient. In this video, we're going to prove these three properties. In order to do that, we have to remind ourselves what the linear MMSE estimator is, which is the best approximation of a random variable B given a random variable A, which is affine, meaning that we are only allowed to scale B and have an additive constant. Okay, in terms of notation, this is the mean of A, mean of B, variances of A and B, and this is the correlation coefficient between A and B. And just to remind you a little bit, this is the minimum MSE estimator, which is obtained by realizing that you can take the standardized version of A, where you subtract the mean and you divide by the standard deviation, which we call like this. And then you can just scale it by the correlation coefficient, and that gives you the best possible estimate of the standardized version of B. And then you just need to map that standardized version of B to an estimate of B by multiplying by the standard deviation and adding the mean. Okay, this is just to remind you of the intuition behind this somewhat complicated affine estimator. All right, now we're going to study the mean squared error of the linear MMSE estimator. And what we're going to see is that this is the key to prove those three properties that I mentioned before. So pay attention. All right, so when we look at the mean squared error, we're comparing basically the quantity we want to estimate, which is B, with its estimate that we have seen can be written like that. So now here, maybe I'll stop, I'll show you this here. Here we can divide and multiply by the standard deviation of B, so that then we can take both of these guys out with a square, because there's a square here. Okay, so this expression is exactly the same as taking out the variance of B and having the mean squared error between the standardized version of B and its optimal linear estimator, which is obtained by just scaling the standardized version of A by the correlation coefficient. So let's expand this out. When we expand this, we get the correlation coefficient squared times the mean square of the standardized variable plus the mean square of the other standardized variable minus 2 times the correlation coefficient times the mean of the product of the standardized variables. So you can look at the previous video if you don't remember this, the one on correlation and covariance, but the standardized variables have 0 mean, unit variance, and hence unit mean square. So this is just equal to 1, this is just equal to 1, and you can easily express the correlation coefficient, and in fact this is how we defined it originally, as the mean, the correlation coefficient between A and B, I mean, as the mean of the product between the standardized variables. Okay, so this is just equal to the correlation coefficient. So this means that in this expression here we have, maybe I'll go back for a moment, rho squared plus 1 minus 2 rho squared. This is just 1 minus rho squared, okay? This is a crucial formula. So let's take a moment to parse it. We're saying that the mean squared error of the best affine estimate of B given A is exactly equal to the variance of B times 1 minus the correlation coefficient between A and B squared. This is going to be absolutely crucial. It's going to enable us to prove these three important properties. Let's go for the first property, which is that the correlation coefficient is always between -1 and 1. We have just proved that the variance times 1 minus the correlation coefficient squared is equal to the mean squared error. But now we realize that the mean squared error can never be negative. Why? Because it's a mean of a non-negative quantity. So basically it's going to be an integral or a sum that only involves non-negative quantities, and then densities or probabilities that are also non-negative. So this is always non-negative. But then this guy cannot be greater or cannot be greater than 1, right? Because then this would be negative, which immediately means that the square of the correlation coefficient is smaller or equal to 1, which immediately implies that the correlation coefficient is between -1 and 1. So that formula immediately gave us this important property, which is that the correlation coefficient of any two random variables is always between -1 and 1. Now, in order to prove the second property, we have to take a small detour. And here I'm just going to state this, but we will prove this a little bit later on in another video in a couple of weeks. If a random variable has 0 mean square, then it is equal to 0 with probability 1. Let's at least provide some intuition. Basically, a random variable with mean square equal to 0 also has variance equal to 0. You can show this because the variance is equal to the mean square minus the square of the mean, and the variance cannot be non-negative. Cannot be negative. So if the mean square is 0, then immediately the variance is 0. If the variance is 0, that means that the random variable is not moving at all. It's equal to a constant, and that constant has to be 0. Okay, this will make a lot more sense when we look at Chebyshev's inequalities later on. But for now, if the mean square is 0, that means that a random variable is 0 with probability 1. Why is this important? It's important because if the correlation coefficient is equal to 1 or -1, then we go back to our formula that gives us the mean squared error. And in this formula, we see that if the square of the correlation coefficient is equal to 1, the mean squared error is 0. The mean squared error is the mean square of this random variable, okay, which is often called the residual. Okay. So if the mean squared of this residual is 0, that means that the residual, this is the residual, okay, what I've called this random variable R, then that means that the residual is 0, and hence B is equal to the linear estimate. But the linear estimate is actually an affine function of A. Here I forgot a squiggly line. Okay, so this immediately shows that when the correlation coefficient is equal to 1 or -1, the two random variables that we're talking about are actually affinely related. There's an affine function that immediately maps A to B deterministically. Okay, so there's complete linear dependence. As usual, I'm saying linear dependence even though the estimator is affine, because you can always center, and people like to talk about linearity more than affineness. All right. So I just want to visualize what I'm talking about. Here we have samples from two random variables that have a correlation coefficient of 0.95. We see, that there's a pretty strong linear dependence, but it's definitely not complete, right? It's not true that for every value of A, you can just map it to a value of B through a linear function. If that were to happen, then the points would lie on a line. So what happens when we push up the correlation coefficient and look at other samples? If the correlation coefficient is equal to 0.99, the samples get closer to the line. 0.999, closer to the line. Eventually, they tend to be almost completely on the line. So that's what we mean by saying that if the correlation coefficient is 1 or -1, then there's exact linear dependence between the two random variables. All right, now let's move on to property 3, which is the one that needs a little bit more work of the three. We want to quantify how much variance is explained by the linear estimate. So the idea is we take the variance of B. I want to see how much of that variance goes into the linear estimator. We'll see why it even makes sense to set things up like that. But before that, we need to, so I was getting ahead of myself and starting to talk about the next slide, but I think it's good to take a moment here to explain this. So when we approximate B using the linear estimate, we also have this residual. What we're going to see is that we can express the variance of B as a sum of the variance of the linear estimate and the variance of the residual. So the more variance the linear estimate has, the less variance the residual has. And we will see that the correlation coefficient immediately tells you this. Immediately tells you the fraction of explained variance in the linear estimate, which essentially tells you how linearly dependent the two random variables are. Okay, hopefully that makes sense. We have to take a little detour to prove this. We're going to look at the variance of a sum of two random variables, A and B. If we write down the formula for the variance of the sum, it's just the sum minus its mean, and then we square, right? But now we can group A and its mean and B and its mean and expand this out. If we do that, we get this expression, then we apply linearity of expectation. Okay, so the means are applied to each of the terms in the sum once we expand it out. What do we have here? This is the variance of A by definition. What do we have here? Variance of B by definition. What do we have here? The covariance between A and B. So the variance of a sum is actually equal to the sum of the variances plus 2 times the covariance between the random variables, which gives us some intuition about what the covariance means. So when there is covariance, the covariance is positive, the two random variables are correlated, then when you sum them up, the interference is constructive, okay, because they're linearly related, the variance is larger than you would expect because there's constructive interference between them. The other way around, if the covariance is negative, when you sum them out, they kind of cancel out when you sum the two random variables, okay? When the covariance is 0, the variance of the sum is just equal to the sum of the variances. And now that's exactly what we're going to use. If A and B are uncorrelated so that their covariance is 0, then the variance of the sum is equal to the sum of the variances because the covariance is 0. This is the important result that we're going to use. Okay, so now we're going to take a look at the residual because we're essentially going to show that the residual and the linear estimator are uncorrelated so that we can decompose the variance of B into the sum of the variances. But let's not get ahead of myself. First, let's take a look at the mean of the residual. We just plug in the expression for the linear estimate. Looks a little bit complicated, but we've seen it so many times that hopefully you're fine with it by now. And when we expand things out, basically realize that when we take the mean of this, it's just equal to the mean of B, it's actually equal to this, so it's just going to cancel out with that. And when we apply linearity of expectation, the only other random variable that we have is here, so we compute its mean, and the means cancel out here. So basically the mean of the residual is 0, which makes sense because if the mean of the residual was not 0, we could always correct for it with the additive constant, right? And get a better linear estimator. Now let's take a look at the covariance between A and the residual. So we have A minus its mean, the residual minus its mean, which is 0, expected value of that product. And now, actually here maybe let's take a look. We can group B and minus mu B and divide and multiply by the standard deviation to get the standardized version of B. And here we can also divide and multiply by the standard deviation of A to get the standardized version of A. Okay, so we have these two guys are coming from the fact that we're multiplying and dividing by those standard deviations. Then we have the standardized version of A and the standardized version of B. Okay, so hopefully that makes sense. And here, by the way, this is just S of A. Okay, if you were wondering where this S of A comes from. Okay, good. So now we expand this out, and what we have is, when we expand this out, the expected value of S of A, S of B is equal to the correlation coefficient of A and B, and the expected value of S of A squared because the variance of the standardized variable is 1 and the mean is 0, the mean square is just equal to 1. All right, so when we plug these things in, we have that the covariance is equal to the standard deviations, the correlation coefficient, minus the correlation coefficient times this mean square, which I just said is equal to 1, so it's 0. We did a lot of math here, but we could have just thought a little bit about this. If you had some covariance in between A and the residual, then you would be able to improve your linear estimator, because what would you do? You would try to use that correlation to add a term to the linear estimator that accounts for part of the residual. But if you were able to do this, you would be able to improve the optimal estimator, and you cannot do this because this is the optimal affine estimator. So all of this to say that it just makes so much sense that A and the residual are uncorrelated, just intuitively, but we have also shown it mathematically. Okay, so now let's go back to this story where we want to show how much variance is explained by the linear estimate. Now we have shown that A and the residual are uncorrelated. But it turns out that when a random variable is uncorrelated with another random variable, any affine function of that random variable is also uncorrelated with the random variable. This is pretty easy to prove using the properties of covariance, and we're going to leave it as an exercise, although we will do something quite similar in one of the following videos when we discuss geometric analysis of correlation. Okay, but for now, let's accept that the residual is uncorrelated with the linear estimate. So then we can apply this decomposition of variance, because these guys are uncorrelated, where the variance of their sum is equal to the sum of the variances. And now it makes sense to ask ourselves how much of the variance goes into this guy and how much of the variance goes into this guy. The more variance goes into the linear estimate, the more linearly dependent A and B are, because you can explain more of B using A. That's the logic. Okay, so what is the variance of the residual? Remember that the residual has 0 mean. We just proved it. So the variance is just equal to the mean square of the residual. What is the mean square of the residual? That's just the mean squared error. So now we can deploy this very important formula that we proved at the beginning, which tells us that this is equal to the variance of B times 1 minus the square of the correlation coefficient. Okay? What does this mean? It means that this guy accounts for a fraction of the variance of B, which is 1 minus the square of the correlation coefficient. How much variance is captured by the linear estimator? Well, the variance is equal to the variance of B minus the variance of the residual, which we know is 1 minus rho squared times the variance of B. So the variance captured by the linear estimator is exactly equal to the square of the correlation coefficient times the variance of B. Okay, and that fraction, okay, of the variance of B is hence equal to the square of the correlation coefficient. That is so important that it has a name. It's its own metric in statistics, which is the R squared, or the coefficient of determination. It's defined as the variance of the best linear estimator divided by the variance of the variable that you want to approximate. And it's exactly equal to the square of the correlation coefficient. Okay, so what does this mean? Well, it means, because we know that the correlation coefficient is between minus 1 and 1, that the coefficient of determination on this R squared is between 0 and 1. When we're at 0, the linear estimator doesn't account for any variance, so the two variables are not linearly related. As we approach 1, the linear estimator accounts for more variance until you reach 1, where the two quantities are completely linearly dependent, as we saw in property 2. Let's take a look at what we actually mean. We have done a lot of math. It's always important to take a step back and look at an example and realize what the different quantities that we're manipulating mathematically actually mean. So let's try to do that. So here we have samples from two random variables that have correlation coefficient equal to 0.75. You see the samples there. This is the linear estimate that we compute based on the correlation coefficient. And this is the residual. So now that what we're saying is that if here you take the variance of the y-coordinate, only the y-coordinate, you will get a histogram of y-coordinates. You can compute the corresponding variance. In this case, it's 1. Now you can do the same for this, okay, for this y coordinates. When you compute the variance, it's equal to 0.56, which is exactly equal to the square of the correlation coefficient. The correlation coefficient immediately tells you how much variance is going to be captured by the linear approximation. And the variance that is left is the variance of the y coordinate here. So what happens if the correlation coefficient is 0.95? Well, we do exactly the same thing, linear estimate, residual. Now what happens is that we know that the variance of the original random variable in here is exactly the same, but the variance captured, the fraction of variance captured by the linear estimate is going to be greater. It's going to be the square of 0.95, and indeed it is. It's approximately 0.9, and the variance captured by the residual is going to be less. What happens if the correlation coefficient is 0? The linear estimator is horizontal. There's no linear relationship between A and B. The residual is actually equal to the original data. And what we see is that no variance is explained by the linear estimate. The variance of the linear estimate is 0 because it's constant, and the residual has the same variance as the original variable. What happens if the correlation is negative? So we have a negative correlation coefficient. Well, it's the same as when we have positive correlation, except that now the estimate is inversely proportional, but in terms of explained variance, it's actually the same thing. So there's the residual, here is the variance of the original variable. If we care about explained variance, it doesn't matter that there's a minus here, because the square of the, I wrote minus 0.5, of course it's plus. I don't know, I try to avoid typos, but they just happen. A square being negative should have been a bit suspicious, you would think. Okay, so of course, this is plus 0.56. It's the same variance as when we had a correlation coefficient of plus 0.75. Okay, and the rest of the variance goes into the residual. Let's see if here I made the same mistake. If you go to minus 0.95, you're explaining more variance with an inversely proportional linear estimate, but still. Here's the residual. Here is the variance of the original samples. This is the variance. Okay, here I did not make the mistake. 90% of the variance is accounted for by the linear estimate, which means that these quantities are much more linearly related than when we had a correlation coefficient of minus 0.75, and hence the variance of the residual is just 10%. Okay, all of this is captured by a single number, which is what's beautiful about this, the correlation coefficient. Let's take a look at some real data. We have proved everything for random variables, but you can actually follow exactly the same arguments, replacing means by sums to show that the sample correlation coefficient is also between -1 and 1, that when it equals 1 or -1, you have complete linear dependence, and that the sample variance also can be decomposed in the same way. I'm not going to go through the arguments because they're almost exactly the same, but I encourage you to do it on your own. So let's take a look at a data set which we have already looked at, where we have the height of NBA players and the number of rebounds, assists, or points per player. And we want to see how these quantities are linearly related. So we had our scatter plot of rebounds against height. The density estimate shows you a little bit better how the data are distributed because a lot of these points are on top of each other. And this was the best linear estimator of rebounds given height. Okay. Now what we're interested is in the variance. So the variance, the sample variance of the rebounds is 6.19. The variance of the linear estimator is 1.10, and the variance of the residual is 5. So it turns out that this variance, the fraction of variance out of the total variance explained by the linear estimator, is exactly equal to the square of the sample correlation coefficient, which is R squared, or the sample coefficient of determination. Okay, just as we proved. So immediately, just by looking at the correlation here, I thought I had written the correlation. I had not written the correlation, but just by looking at the correlation coefficient or its square, we immediately know how much variance is being explained by the linear estimate. In this case, it's 17%, almost 18% of the variance. Let's take a look at assists and height. Here, when you look at the linear estimator, it's inversely proportional. Okay, there's negative correlation between assists and height because shorter players give more passes. When we look at the variance, though, that doesn't matter. We just want to know how much variance is explained by the linear estimator. The variance of assists is 3.21. The variance of the OLS estimator is 0.67, which happens to be around 21% of the total variance here. Okay, and the residual has the rest of the variance. So immediately the correlation coefficient or the coefficient of determination tells you how linearly dependent these two values are. The closer it is to 1, the more linearly dependent they are. The closer they are to 0, the less linearly dependent they are. And this brings me to points and height. This is a scatter plot. This is the density. And this is the OLS estimator, which, we have discussed in previous videos, is almost horizontal. But now we can actually quantify what that means. It means that out of the variance of points per game, 35, the linear estimator accounts for very, very, very little variance, just 3.6% of the variance. So the two quantities are really not linearly dependent. Once you have your linear estimator, you have a lot of uncertainty after you have, the linear model still leaves a residual, which essentially contains almost all of the variance of the original data. Again, that's immediately captured by this single number, which is the correlation coefficient or its square, R squared, or a coefficient of determination. And that's all I got. We have learned 3 very important properties of the correlation coefficient. It's always bounded between -1 and 1. If it is equal to 1 or -1, that implies complete linear dependence between the two quantities of interest. And finally, the square of the correlation coefficient immediately tells you the fraction of variance explained by the best linear estimator. And that's all I got. Thank you very much.